Hello and welcome back. This time we go back to the basics to show how aircrafts work, summarizing an aerospace engineering degree in a few drawings. So, where does the design of an aircraft start from? From a simple sketch of the forces acting on the body. We will consider only the aircraft already in the air that moves in a so-called steady flight, considering maneuvers like takeoff, landing, or instabilities like wind gusts, turbulence, or flutter would require too much math to be drawn. Steady flight means that the aircraft is moving in a straight line at constant speed and without changing altitude. In this condition, a 2D sketch of the aircraft is enough, as there are only four forces acting on the body. Gravity, that pulls it down, and drag, caused by the friction with the air, are the forces that we need to fight against to keep the aircraft moving. To balance the drag, we need engines that provide thrusts that push the aircraft, and wings that generate lift. As you can see, when all forces cancel out, the aircraft and anybody on board feel no force. Let's just have a quick look at the equations to see how they affect each other. Let's start from the weight. We consider fixed the weight of the aircraft, and that is simply the mass of the aircraft itself multiplied by the gravity attraction. Gravity is considered constant since we won't be changing altitude, so the weight will be considered constant, even if in real aircrafts we do account for the fuel we ejected during the flight that reduces it. So now we know the lift required to stay up in the air. It has to be equal to the weight. The equation for lift makes it clear that it depends on the surface area, so more area, more lift, and it goes with the square of the velocity also, so higher speeds allow us to achieve a much higher force pushing us up. The Greek letter ρ is density, and it is constant with the altitude. Finally, the lift coefficient can be obtained, but it can also be considered constant in level flight. With a similar equation, we can describe the drag force acting on the aircraft. Also, the drag coefficient can be considered constant for our scenario. However, now we also know how much drag we need to fight against with our engines. We know the thrusts required. In our ideal case, we want to reduce to the minimum possible weight and drag. We want a light material that reduces weight and is also smooth enough to reduce friction. However, we also want it strong enough to withstand all the forces acting on it. Another way to reduce weight is to efficiently design the structures. This means reducing the material used to withstand all the stresses. Finally, once we have an aircraft capable of staying in the air, we can see how to maneuver it. In control surfaces, seeing how hard it is to make an aircraft turn without falling to the ground. Here, we'll need to consider the aircraft as three-dimensional. This series will only cover the basics of an aircraft design process, considering only the most simple case, but it should be enough to understand how and why aircrafts can fly. After this brief series, we'll do a similar one on rockets, and after that one, we will see how to combine the two concepts on a single machine. Hope you'll stick around for the whole journey. Subscribe and ring the bell to stay tuned. See you next time.